From Newton's first law, we know that an object that is under no external influence moves with zero acceleration, i.e., constant velocity. It follows that if the object is subjected to an external influence, then this influence will cause the acceleration to no longer be zero. The external influence can be a push or a pull on the object in a certain direction. Let's give this external influence a name. Let's call it force. So force is a push or pull on an object in a certain direction. That changes the acceleration of the object. And since acceleration is a vector quantity, i.e., in three-dimensional space it has three independent components in three directions, we expect force also to be a vector quantity. This means that force has three independent components. We will find out in the rest of this chapter that for a force acting on a point particle, each force component affects the corresponding component of acceleration of the particle. Force component 1 affects acceleration component 1. Force component 2 affects acceleration component 2. And force component 3 affects acceleration component 3. Next we will conduct some experiments to derive a mathematical expression for force. Let's design an experiment to find a relation between force and acceleration. Let's place a puck on the shown linear 1D frictionless rail and connect it to a spring that is fixed at one end to the puck, and at the other end is fixed to the frame of the rail. We'll use a ruler to measure the position of the puck on the rail. We'll start with the rail being horizontal, and note the position of the puck on the rail, when the puck is at rest. Then we'll change the inclination angle of the rail, and record the position of the puck on the rail as a function of the inclination angle. Just like in the previous rail experiments, there are no solid obstructions along the path is frictionless, air resistance is negligible, and there are no electrical or magnetic effects acting on the puck. When the rail is horizontal, there is no gravity influence acting on the puck. And since the puck is at rest, its acceleration is zero. This means that the spring is not exerting any influence on the puck. If it were exerting an influence, the acceleration wouldn't be zero. When the rail is at an inclined angle, the only influences on the puck are gravity and the spring. And again, since the acceleration of the puck is zero when the puck is at rest, this means that gravity and the spring influences must be cancelling each other out. So in summary, when the puck is at rest, if the rail is horizontal, there are no influences on the puck. And if the rail is inclined, there are two influences, namely gravity and the spring, and the two are equal in magnitude and opposite in direction. Now let's perform the experiment and record the results in the shown table. In the first column we will record the inclination angle, theta, in degrees. The second column will be g times the sine of the inclination angle, where g is the acceleration of gravity, 9.8 meters per second squared. And g sine theta is the value of the acceleration of the puck due to gravity, if the puck was not attached to the spring. As we have seen in the one-dimensional kinematics chapter, the acceleration of a puck that is moving on a frictionless inclined rail, such that the puck is only under the influence of gravity, is equal to g sine theta. In other words, g sine theta measures the magnitude of the gravity influence on the puck. In the third column, we will tabulate the position of the puck after it comes to rest. And the last column will be the deflection, which we define as the position at theta, minus the position when the inclination angle is zero. In addition, we will plot g sine theta versus the position of the puck, and g sine theta versus the deflection of the spring. First we set the inclination angle to 0 degrees, in other words the rail is horizontal. And we use the ruler to measure the position of the puck on the rail. And as you can see from the shown chart, the position of the puck is 0.402 meters. And so the deflection is 0.402 minus 0.402 or 0. And we plot the points on the graph as shown. Then we set the inclination angle to 5 degrees. And wait until the puck comes to rest. And we see that the position of the puck is 0.426. The deflection is therefore 0.426 minus 0.402 or 0.024. And we plot the points on the graph as shown. Next we set the inclination angle to 10 degrees. And wait until the puck comes to rest. And we see that the position of the puck is 0.449. The deflection is therefore 0.449 minus 0.402 or 0.047. And we plot the points on the graph as shown. Then we set the inclination angle to 15 degrees. And wait until the puck comes to rest. And we see that the position of the puck is 0.472. The deflection is therefore 0.472 minus 0.402 or 0.070. And we plot the points on the graph as shown. We continue changing the inclination angle until we get to an angle of 90 degrees. At which the puck is at a resting position of 0.677, and a deflection of 0.677 minus 0.402, or 0.275. And we plot the points on the graph as shown. Connecting the points, we see that the plot of g sine theta versus the position of the puck is a straight line. And also the plot of g sine theta versus the deflection of the spring is a straight line. There are two forces acting on the puck. The spring is pulling the puck up, along the direction of the spring. And the gravity force is pulling the puck down, in the opposite direction of the spring force. Since the puck is at rest, in other words its acceleration is 0. Therefore, both forces must be equal in magnitude and opposite in direction, such that they cancel each other out. We assume that we are using a linear spring, therefore, the spring force is linearly proportional to minus the deflection of the spring. We must use a minus sign in front of the deflection because Fs pulls the puck up in the direction of negative x, while d increases in the direction of positive x. But, we know that the spring force and gravity force are equal in magnitude and opposite in direction. Therefore, the gravity force is linearly proportional to the deflection of the spring. From our experiment, we can see from the plot of g sine theta versus deflection that g sine theta is linearly proportional to the deflection. And so we know that Fg is proportional to d, and g sine theta is also proportional to d. Therefore, the gravity force is linearly proportional to g sine theta. Recall that g sine theta is the acceleration of the puck, if the puck was free to move without the influence of a spring. Then, from equations 3 and 4, we conclude that Fg is proportional to Ag. In general, we conclude that for a body in a gravity field, the magnitude of the gravity force is proportional to the acceleration of the body in the gravity field, if the body was free to move without another external influence, such as the spring. When the rail is horizontal, changing the mass of the puck has no effect on the position of the puck on the rail. In other words, the position of the puck is the same for any mass of the puck when the rail inclination angle is 0. We can try this experiment now. Let's set the rail to be horizontal. And set the mass of the puck to be 0.1 kilograms. And measure the position of the puck. And we see that its position is 0.402. Next we set the mass to be 0.3 kilograms. And measure the puck's position. And find that its position is still 0.402. We can try it again with a mass of 0.6 kilograms. And we get the same result. Thus we see that changing the mass of the puck has no effect on the puck's position, when the rail is horizontal. Let's design an experiment to find a relation between force and mass. Just like in the previous experiment, we place a puck on the shown linear 1D frictionless rail and connect it to a spring that is fixed at one end to the puck, and at the other end is fixed to the frame of the rail. We'll fix the inclination angle at 45 degrees, as shown here. We'll start with a mass of 0.1 kilograms for the puck. And we'll use the ruler to measure the position of the puck on the rail. Then we'll change the mass of the puck, in increments of 0.1 kilograms. And measure the position of the puck on the rail. We'll record in a table the mass of the puck in kilograms, the position of the puck on the rail in meters, and the deflection of the spring in meters. The deflection is equal to the position of the puck, minus the position of the puck at theta equals 0. As we saw from the previous experiment, the position of the puck at theta equals 0, is 0.402. We'll also plot mass versus the position of the puck, and mass versus the deflection of the spring. Now let's perform the experiment. The inclination angle of the rail is set to 45 degrees. We start with the mass of the puck equal to 0.1 kilograms. And we measure the position of the puck on the rail as 0.441 meters. The deflection is therefore equal to 0.441. Minus the position when the rail is horizontal, which is 0.402. And so the deflection of the spring is equal to 0.039. And we plot the points on the graph as shown. Then we change the mass of the puck to 0.2 kilograms, and repeat the experiment. And find that the position of the puck is equal to 0.479. The deflection is therefore 0.479. Minus 0.402. Or 0.077. And we plot the points on the graph as shown. Then we change the mass of the puck to 0.3 kilograms. And find that the position of the puck is now equal to 0.518. The deflection is thus 0.518. Minus 0.402. Or 0.116. And we plot the points on the graph as shown. We continue changing the mass until we get to a mass of 1 kilogram, at which the puck is at a resting position of 0.787, and a deflection of 0.787 minus 0.402, or 0.385. And we plot the points on the graph as shown. Connecting the points, we see that the plot of mass versus the position of the puck is a straight line. And also the plot of mass versus the deflection of the spring is a straight line. There are two forces acting on the puck. The spring is pulling the puck up, along the direction of the spring. And the gravity force is pulling the puck down, in the opposite direction of the spring force. Since the puck is at rest, in other words its acceleration is 0. Therefore, both forces must be equal in magnitude and opposite in direction, such that they cancel each other out. We assume that we are using a linear spring, therefore, the spring force is linearly proportional to minus the deflection of the spring. We must use a minus sign in front of the deflection because Fs pulls the puck up in the direction of negative x, while d increases in the direction of positive x. But, we know that the spring force and gravity force are equal in magnitude and opposite in direction. Therefore, the gravity force is linearly proportional to the deflection of the spring. From our experiment, we can see from the plot of mass versus deflection that mass is linearly proportional to the deflection. And so we know that Fg is proportional to d, and m is also proportional to d. Therefore, the gravity force is linearly proportional to m. In general, we conclude that for a body in a gravity field, the magnitude of the gravity force is proportional to the mass of the body. From experiment 1, we found that force due to gravity on a body is linearly proportional to the potential acceleration of the body due to gravity if the body was free to move with only gravity as an external influence. Let us call this acceleration simply the potential acceleration due to gravity since the body is not actually moving. The potential acceleration due to gravity is equal to g times the sine of the inclination angle of the rail. From experiment 2, we found that force due to gravity on a body is linearly proportional to the mass of the body. Therefore, the gravity force is linearly proportional to the product of the mass and potential acceleration due to gravity. Thus, we can write an equation for the gravity force as Fg is equal to a constant c, times mass times potential acceleration due to gravity. If we set this constant by definition to be 1, then, the gravity force Fg is equal to mass times the potential acceleration due to gravity. Next, we are going to use this equation to come up with a definition for force. If the inclination angle of the rail is equal to 90 degrees, then sine theta is equal to 1. Which means that Ag is equal to g. And Fg is therefore equal to m times g. We define this force as the weight of the body. Note that if theta is equal to 90 degrees, then the rail is not influencing the puck in any way. So we can remove the rail, and just have the spring and the mass. We just derived an expression for one type of force, namely the force due to gravity on a body of mass m. We found that this force is equal to the mass of the body, m, times the potential acceleration due to gravity, ag. We can take this expression of the gravity force to be the definition of force. For example, if you are holding an object in your hand, then that object is exerting a downward force on your hand, which is equal to the gravity force of the object, which is the weight of the object. Note that the object is not moving or accelerating. If you let the object fall, then it will fall with an acceleration equal to the acceleration of gravity. The force of gravity is equal to the mass of the object times that potential acceleration. So we define force in general as a push or pull on an object that can give that object of mass m a potential acceleration a, such that the value of the force F is equal to m times a. As we have already seen, force is defined as mass times acceleration. In the SI system, the units of mass is kilograms, and the units of acceleration is meters per second squared. Therefore force is in units of kilograms, times meters per second squared. This is defined as units of newtons, abbreviated as capital N. So 1 Newton is equal to 1 kilogram times 1 meter per second squared. In other words, 1 Newton is the amount of force that, if applied on a body of 1 kilogram mass, will give it an acceleration of 1 meter per second squared. Since acceleration is a vector quantity, then force is also a vector quantity. In component form, this equation can be written in 3 dimensions, as Fx is equal to m times ax, Fy is equal to m times ay, and Fz is equal to m times az, and in 2 dimensions, as Fx is equal to m times ax, and Fy is equal to m times ay, and in 1 dimension, as Fx is equal to m times ax. In this example, we have a block of mass 2 kilograms resting on an inclined plane. The inclination angle of the plane, theta, is equal to -20 degrees. Let's calculate the gravity force parallel to the plane, acting on this block. Recall that the magnitude of the potential acceleration due to gravity of an object on an inclined plane is equal to the absolute value of g sine theta, where g is the vertical acceleration of gravity in the negative y direction, and theta is the inclination angle of the plane. Note that this acceleration vector is in a direction parallel to the plane. The magnitude of vector ag evaluates to the absolute value of 9.81 times the sine of -20 degrees, which is equal to 3.355 meters per second squared. The x component of vector ag is therefore equal to the magnitude of ag times cosine theta, which evaluates to 3.153 meters per second squared. The y component of vector ag is equal to the magnitude of ag times sine theta, and evaluates to -1.147 meters per second squared. The gravity force vector parallel to the plane is equal to the mass times the acceleration vector parallel to the plane. This evaluates to a force parallel to the plane that has an x component of 6.31 newtons, and a y component of -2.30 newtons. If the mass of a body is 0.5 kilograms, and its potential acceleration due to gravity is 2 meters per second squared in the x direction, and 1 meter per second squared in the y direction, then the force vector is equal to the mass of 0.5 times the acceleration vector 2, 1, which equals a force of 1 newton in the x direction, and 0.5 newtons in the y direction. In this example, the mass of the body is 0.5 kilograms, and the potential acceleration due to gravity is 0 meters per second squared in the x direction, and -9.8 meters per second squared in the y direction. The force vector is therefore equal to the mass of 0.5 times the acceleration vector 0, -9.8, which equals a force of 0 in the x direction, and -4.9 newtons in the y direction. Since force is a vector quantity, then if there are multiple forces acting at one point on the same body, such as forces F1, F2, F3, and F4 shown here, then the net force, also known as the resultant force, is the vector sum of all the forces F1 plus F2 plus F3 plus F4 is equal to the resultant, Fr. Click on the shown link if you'd like to review the section on vector addition. Suppose we have three forces acting on a body, as shown in the figure. Force F1, Force F2, and Force F3. The resultant Fr is equal to the sum of vectors F1, F2, and F3, which is 84.85, 84.85 newtons, plus 43.30, minus 25 newtons, plus 0, minus 80 newtons, which is equal to 128.15, minus 20.15 newtons. Graphically we can find the resultant by drawing vector F1. Then from the tip of vector F1, draw vector F2. And finally from the tip of vector F2, draw vector F3. The resultant is the vector from the root of vector F1, to the tip of vector F3. We are given a body of mass m0, connected using ropes and frictionless pulleys, to three bodies of masses m1, m2, and m3 as shown. The ropes and pulleys have negligible masses. The rope, connected to mass 1, is pulling mass m0 at an angle of theta1 as shown. The rope, connected to mass 2, is pulling mass m0 at an angle of theta2 as shown. And the rope, connected to mass 3, is pulling mass m0 at an angle of theta3 as shown. Given the masses and angles in the table, find the resultant force vector on mass m0. First we calculate the magnitude of the force vectors. The magnitude of force vector F0 is mass m0, which is 1 kg, times g, which is equal to 9.81 newtons. Since the ropes and pulleys have negligible masses and the pulleys are frictionless, therefore, the magnitude of the force at any point in a rope is the same. Therefore, the magnitude of force vector F1 is equal to mass m1, which is 0.8 kilograms, times g, which is equal to 7.848 newtons. In the same manner, we calculate the magnitude of F2 to be 12.753 newtons, and the magnitude of F3 to be 11.772 newtons. Then force vector F0 has an x component equal to the magnitude of F0 times the cosine of theta0, and a y component equal to the magnitude of F0 times the sine of theta0. And so we find that vector F0 is 0, minus 9.81. Similarly the force vector F1 has an x component equal to the magnitude of F1 times the cosine of theta1, and a y component equal to the magnitude of F1 times the sine of theta1. And so we find that vector F1 is 3.92, minus 6.80. Similarly, we find vector F2 is 0, 12.753. And vector F3 is minus 10.19, 5.886. The resultant force vector is the sum of all the forces acting on mass m0, and is equal to F0 plus F1 plus F2 plus F3, which is equal to minus 6.27, 2.029. Forces can be divided into non-contact forces and contact forces. Non-contact forces are forces that act on a body without direct contact with another body. Examples of non-contact forces include the following. Gravity force. For instance, the gravity force between the Earth and the Moon that is equal to 1.98 times 10 to the power 20 newtons. Magnetic force is a force on a magnetic material, without a magnet being in direct contact with the body. Electric force. For example, if you rub a rubber bar with fur, it can attract a styrofoam peanut. Examples of contact forces include the following. A spring force. A spring exerts a force on a mass, equal to the deflection of the spring, times a spring constant. A normal reaction force. For example, a cue hitting a ball. Rope force. For example, if we pull a body with a rope, then the rope exerts a force on the body. Pressure force. For example, if we have a piston, and a cylinder filled with gas, then the gas exerts a force on the piston, pushing it upwards. Friction force. For example, if an object is sliding on a rough surface, then the interaction between the rough surface and the object results in a force between the two objects that opposes the motion. You may click on any of the links shown here to review that section. To get a feel for what a force is, let's look at the range of values of various physical forces. The gravitational force between the Sun and Jupiter is 4 × 10⁻³ newtons. The gravitational force between the Earth and Moon is 2 × 10⁻20 newtons. The thrust force of the Space Shuttle during launch is 3 × 10⁷ newtons. The weight of an elephant is 50,000 newtons. The weight of an average human being is 840 newtons. The weight of a cat is 30 newtons. The weight of a fly is 1 × 10⁻⁴ newtons. The weight of a grain of sand is 2.5 × 10⁻⁵ newtons. The electric attraction between a proton and electron in a hydrogen atom is 2.3 × 10⁻8 newtons. The weight of a human cell is 1 × 10⁻11 newtons. The weight of a hydrogen atom is 1.6 × 10⁻26 newtons. The weight of an electron is 9 × 10⁻30 newtons. And finally, the gravitational attraction between a proton and electron in a hydrogen atom is 3.6 × 10⁻47 newtons.